Kristine DeLong, an associate professor in the Department of Geography and Anthropology at Louisiana State University, and I am a paleoclimatologist who studies natural climate variability. I also work in the South Central Climate Science Center. In this video, I'll discuss the different modes of natural climate variability from instrumental records and paleoclimate archives. During the past 2.5 million years, the Earth has undergone cycles of glaciation, or the ice ages. These large glaciation events were driven by changes in the Earth's orbit around the Sun, the tilt of the Earth's rotation axis, and the wobble of the Earth as it rotates on its axis, similar to a spinning top. In the 1920s, Milankovitch calculated the Earth's orbit, tilt, and wobble back in time and hypothesized that cyclic changes in these orbital parameters caused the ice ages. Paleoclimatic records from the ice cores and marine sediment cores confirmed these Milankovitch cycles in the later 20th century. The Earth rotates every day on its axis, giving us night and day, and it revolves around the Sun once a year. Our seasons occur because the Earth tilts on its rotational axis, such that one hemisphere gets more direct sunlight than the other during its summer. The current angle of the Earth's tilt is 23.5 degrees. The tilt of the Earth varies from 22.1 to 24.5 degrees every 41,000 years. As the angle of the Earth's tilt increases, seasons become more extreme, especially in the higher latitudes where ice sheets form. Currently, the tilt is decreasing, which is not favorable for ice sheets to form. In addition, the shape of the Earth's orbit around the Sun varies from an oval shape to nearly circular every 100,000 years. Currently, it's becoming more circular, a condition that does not promote ice sheet growth. Furthermore, the wobble of the rotating Earth causes the timing of the equinoxes to shift in orbital position around the Sun every 21,000 years. Combining the shape of the Earth's orbit with its precession of the equinoxes results in an orbital configuration where the northern hemisphere summer currently occurs when the Earth is furthest from the Sun. This condition helps to form ice sheets. Milankovitch found that for ice sheets to grow in North America and Eurasia, the optimal configuration of these three orbital parameters is such that the total energy from the Sun at 65 degrees north is too low for ice sheets to melt during the summer. Along with the Milankovitch cycles, the Sun itself has changed in the amount of energy it is producing. These changes are closely linked to sunspots that increase in number every 11 years or so. Sunspot cycles cause little change in the amount of energy reaching the top of the Earth's atmosphere, less than 0.1%. Some studies show that the Little Ice Age in Europe from 1300 to 1850 coincided with periods of low sunspot activity called the Dalton and Maunder minimums. However, compilations of many paleoclimatic records show that the Little Ice Age did not occur worldwide, and the cold events did not occur at the same time in different regions. Furthermore, from 2006 to 2010, sunspots were at a minimum, yet global temperatures continued to rise. Besides these changes in the Earth's orbit and the Sun's energy, climatologists have found other types of natural climate variability that tend to occur at regular intervals. These cycles are generally not global in extent, but can have impacts in adjacent regions. The strongest of this type of climate variability is the El Niño Southern Oscillation, or ENSO. ENSO events occur in the tropical Pacific Ocean every 3 to 7 years and are seen as regional changes in sea surface temperatures driven by changes in the strength of the trade winds. In normal conditions, the trade winds blow from the east, moving ocean surface waters from the east to the west across the Pacific Basin. This motion causes upwelling of colder water from the ocean's depths to the surface along the equator and the western coast of South America. Warm waters are pushed towards the western Pacific, where they are blocked by large equatorial islands, including those in the Philippines and Indonesia. An enormous warm water pool develops there, accompanied by tremendous amounts of evaporation and precipitation. This strong convection causes a vertical circulation with winds at high altitude flowing from the west to the east and descending in the eastern equatorial Pacific. During El Niño events, the trade winds weaken and the tropical surface waters do not move to the west, and upwelling does not occur. Thus, El Niño causes the eastern Pacific to become warmer than normal. and the normally dry regions of North and South America get tremendous amounts of rainfall. And the Western Pacific experiences lower rainfall and heat waves and large forest fires in Southeast Asia and Australia. During El Niño events, many coral reefs in the Western Pacific and Indian Oceans bleach from warmer waters and no clouds, with many corals dying if the waters do not cool quickly. La Niña is the opposite event of El Niño. It amplifies the normal conditions, strengthening the trade winds. Both of these ENSO events have far-reaching influences even to North America and Europe. Besides ENSO events, there are several modes of climate variability that occur on multidecadal timescales in the Atlantic and Pacific Oceans. The Pacific Decadal Oscillation, or PDO, occurs in the North Pacific, with warmer waters switching to colder waters every 20 to 30 years, leading to changes in fisheries. The Atlantic Multidecadal Oscillation, or AMO, is a warming and cooling cycle in the North Atlantic Ocean that occurs every 50 to 90 years. The warm phase of the AMO has been linked to an increase in Atlantic hurricanes. Paleoclimatologists are working to reconstruct these so-called oscillations before the 20th century, when instrumental temperature records are sparse. However, their reconstructions tend to not agree with each other, or they find the cycles do not occur regularly. Many researchers have stopped calling these oscillations because they do not appear to be constant periodic fluctuations. Instead, we refer to them as multidecadal variability. In my research, I examined multidecadal variability in the tropical Southwest Pacific and the Gulf of Mexico using large boulder-shaped corals that live for 300 to 400 years. What I've learned from the Southwest Pacific corals is that there are multidecadal climate variations before the 20th century that are different from the PDO. In this case, these variations occur every 20 to 25 years, but shift to 30 to 40 years before the 20th century. These shifts in decadal temperature variability coincide with large-scale changes in ocean circulation and precipitation since the start of the 20th century. Understanding natural climate variability in our climate before the industrial age is important because it allows scientists to better understand how the undisturbed climate system functions with time and space. This understanding will help us forecast future climatic changes on regional to global scales.